This video will look at 6 different types of reactions. These are reactions that you will encounter throughout this course. These are reactions that you need to be able to identify. So the first 2 reactions are related to one another. So the first one is a synthesis. It's also called a composition or a combination reaction. They all basically mean the same thing. I'm taking 2 or more reactants and I'm creating a product or products that are a combination or composed of or made up of my reactants smashed together. So there are 2 different ways that we will often look at them. One is an ionic compound. I create an ionic compound. So when I create an ionic compound, the charges must be balanced. So I have to create an ionic compound that is neutral in charge. So I have magnesium and nitrogen, and they combine to form magnesium nitride. Now notice that the subscripts don't necessarily carry over. The subscripts in the reactants really have nothing to do with what they are in the products. You may have a subscript that's the same, but that's actually just coincidence. So you'll see that I have this general form of A plus B yielding AB, magnesium and nitrogen, and I'm creating a compound made up of the 2 of them. Another example, molecular, this may be something you're familiar with. I take carbon dioxide and water, and I create a larger, more complex molecule out of them, C6H12O6, and oh, by the way, I have some oxygen left over. This is photosynthesis. Neither of these equations are balanced. We're just trying to show you the general overall format. I have simpler, smaller reactants creating larger, more complex products. The second reaction is related to the first one, and you can tell that by the name. So one of the names of this is a decomposition reaction. So the reason why I usually call the first one a composition is because it's to show that the decomposition reaction is really just the opposite of it. So I'm taking a larger complex reactant and I'm breaking it up into smaller, simpler parts. Oftentimes this will require special aspects of my reaction to be true. So I'm taking my ionic compound, magnesium nitride, and I'm creating magnesium and nitrogen. Again, it's not balanced. But what you see over this arrow is a triangle or a zigzag lightning shape. These are 2 things that tell you that this reaction must be done under the conditions of, and the triangle means heat, so I have to heat this compound up, or I have to zap it with electricity. So anything that goes above or below the arrow tells you that there are special conditions that have to be in place. So again, I create substances that actually exist. So this has the subscript of 2 because it's a Brinkelhoff element, it's diatomic. Again, I have to create things that exist. And then this is just the decomposition of glucose, C6H12O6, in the presence of oxygen. I require an enzyme or a catalyst, and I create carbon dioxide and water. So this is what happens in our body when we combust our food. So the point of a decomposition reaction is that it's the opposite from a composition reaction. Oftentimes ionic compounds need to be exposed to heat, which we show with a triangle, or electricity, which we show with the zapping sign. And molecular compounds, in order to decompose, often need an enzyme or a catalyst in order for that to happen. So those are the first 2 of the 6 reactions. The second 2 are not related to one another. They kind of stand alone. And the first one is a combustion reaction. So a combustion reaction has the general format of I'm taking my reactant and I'm doing it in the presence of oxygen gas. And I usually create my first element, O2, and then my second element, B2O. So here are a couple of examples that help clarify this. So this is CH4 plus O2 creates C, which is that first element, O2, and B, which is the H, H2O. So I'm taking, this is my A and this is my B element, and I'm joining it with O2 and O. Try this with N2H2 in oxygen, and I create NO2 and H2O. Remember that these subscripts don't necessarily carry over. I have to create compounds that actually exist. So I can't say it like H4O or H4O2. Sometimes I'm combusting just singular elements, and usually they create things that you're familiar with. For example, carbon in the presence of oxygen will create carbon dioxide, and H2 and O2 will create H2O. One of the things about a combustion reaction is that it requires oxygen gas as a reactant, and it's exothermic and creates a huge amount of heat energy. The fourth reaction is a dissociation reaction. So a dissociation reaction uses an ionic compound, and it's acting in the presence of water. Water is not a reactant because it actually doesn't get changed, and it creates ions. So I'm separating the ions out in an ionic compound. So I'm not creating, I'm creating positive and negative charges, and the positive and negative charges have to be actual charges that exist. So one thing that you'll notice, so I have NaCl creating Na plus and Cl minus ions, is that I have to have certain subscripts. So ionic compounds at room temperature are always solids. And when I have aqueous ions in dissociation, I have to have the AQ subscript next to each of my products. I also have to give the charge, and the charge is ending up having to balance. And then you'll notice that the subscripts here end up being the coefficients here. So if I have Mg3 and 2, I'm going to create 3Mg plus 2N minus 3. The subscripts, again, do not carry over to this side, but they often will become coefficients when they are dissociating. So ionic compounds have to dissolve in water. They create aqueous ions, so the charge and the AQ have to be there, and the ion charges have to be real. So one thing to notice is that dissociation and decomposition look very similar, right? So I'm taking AB, and I'm creating A and B by themselves. The difference really is that here I'm doing it in the presence of water for dissociation and creating aqueous ions. And decomposition, I'm doing it in the presence of heat or electricity, and these are not aqueous and they are not ions. So they look similar, and it's very easy to confuse them at first, but they are very different reactions. The final two reactions are related to one another, in which they are called replacement or displacement reactions. So the general format is that things will switch partners. So think of it like a dance. In the single replacement reaction, you have two ions that are here, and then one element will replace one of the partners. So here I have AB plus X, and the X is switching places with the A, so now X is with B and A is left alone. Or I might have AB and Y switches places with B, and in that case I now have A with Y and B stands alone. So here X is going to be a metal replacing the metal that's A, and here Y is the non-metal that switches places with B. So examples of the first one where the metals switch is silver nitrate and copper, where copper and the silver switch places, and I leave silver by itself. Or if non-metals switch, lithium bromide with fluorine gas, the fluorine and the bromine switch places, and so now LiF is with each other and Br is by itself. Again, you have to create products that actually exist. So ionic compounds have to be balanced, and if I have something that's a Brinkelhoff, a diatomic element, I have to make sure that I create those as well. So those are extra things to think of. One of the things that's true about all displacement or replacement reactions is that all of the ionic reactants, the things on the left-hand side, ionic reactants, must be aqueous. So you'll notice that here I have AQ, here and here, because they are reactants and they are ionic. One of the products has to be a solid, a liquid, or a gas, right? So here, my solid here is my silver. I have a liquid here that's bromine. Sometimes I might create something like nitrogen gas or oxygen gas. And one of the products must be an ionic compound. And we're not sure whether or not they're aqueous or not. You don't have to worry about the product state of matter. And just a reminder that whenever you have ionic compounds, whether it's as a reactant or a product, the charges have to balance. You can't just carry subscripts over. A double replacement reaction is just the same as a single replacement reaction, but now both couples are switching partners. So the general format is AB plus XY, and now the A's matched up with the Y, and the X is matched up with the B. So the metals always have to be in front, so the X and the A are both in the front, and the B and the Y are second. These are all ionic compounds, so the charges have to balance. So same thing with a single replacement reaction. All of the ionic reactants must be aqueous. So aqueous, 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 aqueous. And the products are also ionic compounds, so the charges have to balance. So even though I have just one sodium here, I have to have two sodiums here because it's balancing with sulfate ion, and so it's going to have Na2SO4. And one of the products must either be a solid, like silver chloride in the first reaction, or water in the second reaction. So those are the 6 types of reactions that you will have to be able to start to identify. And every time we talk about reactions, we will first be talking about what type of reaction it is in order to orient you so that it just becomes second nature to be able to identify those reactions.